Hello and welcome to what should be the final lecture that we're going to have regarding polynomial functions. Now we're going to deal with polynomial functions as they exist in rational functions. So we're going to have to be graphing them. And in these rational functions, it's going to be some polynomial term A over some polynomial term B. We're going to refer to the rectangular hyperbola, shape, but there could also be some differences. So we're going to go ahead and we're going to graph three of these rational functions, and the steps to do so are pretty simple. First, we find asymptotes. Then we determine quadrants. I'm going to put these as quotations because that's not technically what they're called, but it's what I'm going to call them. And then all right, I do apologize for that that interruption, but I do suppose that I figured out the problem for my whatever. Just move on. Okay. So first we have to find the asymptotes, then we determine the quadrants of the asymptotes, and I use that term lightly, but you'll determine why, and then we're good to go. So finding the asymptotes is easier said than done. So let's just find a couple examples to figure out how many asymptotes we have. We can have surplus asymptotes. We can have more than one vertical asymptote. Keep in mind, we can have more than one vertical asymptote, but we can only have one horizontal asymptote. And an asymptote is basically a point on the graph at which, point in a graph, you remember the rectangular hyperbola, the asymptote is a point at which the graph hits but never gets to. Approaches but never gets to, rather. So the first example I'm going to use is 2x over x minus 3. And the first things first, to find the vertical asymptote, what we're going to do is we're going to find when the bottom equation equals 0. So x minus 3, when does it equal 0? It equals 0 when x equals 3. And why does this matter? What do we get by knowing that the graph equals when x equals 3, the graph equals 0? Well, because of the rule of dividing by 0, we know that our denominator cannot equal 0. So we just gotta simply look for the situation for the point at which x does equal 0, which is at 3. So this point will never, this graph that we're gonna draw is never gonna touch x equals 3. So if I can go 1, 2, 3, we're gonna have our vertical asymptote right there. Our vertical asymptote is basically an asymptote that describes an x-axis. So that's how I find our vertical asymptote. And remember, the vertical asymptote versus horizontal asymptote, just think about how the equations would look. X minus 3 will go up and down. That's vertical. Versus a y asymptote will just go left to right. Now, to find a y asymptote, easiest put, we look at the fastest growing terms on each side. So this is a constant. This is actually disregardable. Remember when we looked at end behavior and we saw that as the numbers got really big, all we'd have to look at was the highest growing term or the largest term, which is exactly what we must do in this situation here as well. We look at the two fastest growing terms, which in this situation are x and x. And now, rules for horizontal asymptotes. Horizontal asymptotes are a little different. They're a little different than vertical asymptotes. And the rules are, if the numerator's degree equals the denominator's degree, then all you got to do is just divide them out. If the numerator's degree is greater than or equal to the, numerator's degree is, hold on, let me gather my thoughts real quickly, guys. It has to be if the denominator is equal to or greater than the numerator is what it is. Yes. If the denominator, let me write that out in words. If denominator is equal or greater than numerator, then we have ourselves our horizontal asymptote. So if denominator is greater than or equal to the numerator, then we have a horizontal asymptote. However, if the denominator is less than the numerator, then we have something called an oblique asymptote. So in this situation, since the denominator 2x over x minus 3 is equal to the numerator, then we have a horizontal asymptote. And then what we got to do is we simply divide the fastest growing terms. So the coefficients of the fastest growing term rather. So 2 over 1 is 2. So our horizontal asymptote is y equals 2. And the reasons of this, well, you could experiment it. Let me not do that. Let's draw a dotted line best we can. And now we've graphed our asymptotes. So y equals 2. And now what we have to do is we have to determine where these asymptotes are going to, where these functions are going to exist. Recall the rectangular hyperbola had two ones going like that. So now what we got to do is we just got to pick a point. So let's pick 0. 2 to the 0, 2 times 0 is 0, and 0 over anything is going to be 0. So our point's going to exist over here. So we're going to go in this direction, up here, and in this direction, down here. Now we got to pick another point. Let's pick 4. 2 times 4, 4 will be over here. 2 times 4 is 8. 8 over 3 is 5. So is 5 above our horizontal asymptote? You bet. So then our equation looks something like that. And we've graphed our first example. Let's graph another example. Each of these examples, by the way, is going to be different. And there's a reason for all of them. Now, y equals, let's draw a line. Y equals x squared over x squared minus 16. And we have to graph this. First step is to find our asymptotes. So let's find an asymptote. Let's find our vertical asymptotes. That's when the denominator is equal to 0. Recall that the vertical asymptote is the x values, the values for x that cannot exist. So x cannot be equal to the following values. So x squared minus 16 equals 0. Well, in this situation, we're going to have more than one asymptote. We're going to have x equals plus or minus 4. We're going to have two situations. We can't have x equal 4 or negative 4. So then on our graph, the first thing we're going to want to do is label these asymptotes. So 1, 2, 3, 4. That's one. That's one that we can't have. X equals 4. And then negative 1, negative 2, negative 3, negative 4. That's another one. And I know I did a terrible job of graphing these nice and even. So that's x equals negative 4. And that's the vertical asymptote. We found the vertical asymptote. Now we got to find the horizontal asymptote. Well, look over here. The denominator is greater than the numerator. The denominator is indeed equal to the numerator in this situation. So we just do the coefficients of each. 1 divided by 1 is 1. So our horizontal asymptote is y equals 1. Y equals 1. And then from there, it's a simple point of trying to see in each of these quadrants. When I said quadrants, I wanted to save this for this discussion. These are different quadrants. Up here, down here, or up here. Now, for it to be a function, recall that a function has to pass the vertical line test. Meaning, they can't have two overlapping each other. So one has to exist up here or up here. And another one has to exist in this quadrant, up here or down here. And then so on and so forth. Let me redraw that without those lines in the middle, because that seems to be a little bit confusing. So let me just, yes, do that. And then negative 4 somewhere over here. And then positive 4 somewhere over here. And that's a gross approximation, but it's good enough. So now we can only have one line curve over here. And since this equals x equals negative 4, x equals positive 4, and then y equals 1. It's simply a matter of putting in equations and testing it out. So now, let's do negative 5. Negative 5 squared is 25. 25 over 25 squared. 25 squared is 25 squared is 625 minus 16 is 609. So at this situation, it's going to be 609. And is 609 above 1? You're damn straight it is. So now what's going to happen is it's going to hug this part of the graph. Now let's choose a different one. Let's choose 0, 0. 0, 0 is a good one. 0 squared is 0. So in that situation again, my friends, it's going to be the one that uses this now. And lastly, let's do 5, regular 5. Well, 5 squared is 25. It's the exact same problem as previously described because of squaring. So that's, and we successfully graphed B. Lastly, let's graph our last equation. Okay, we're at 10 minutes. We're pretty good. Y equals x squared plus 4x minus 12 over x minus, sorry again for the cut, x minus 6. First things first, we got to find our asymptotes. Let's start with the vertical again. X minus 6 equals 0. That's only when x is at 6. So we only are going to have one asymptote, which is going to be 1, 2, 3, 4, 5, 6. Let me draw that asymptote now. So that's the first step. We have to dot our asymptotes. X equals 6. Now to figure out whether we have a vertical asymptote or oblique asymptote, we got to look. Okay, this is the largest term over here. This is the largest degree term, x squared and x to the first. Well, the degree of the denominator is less than the numerator, so we have ourselves an oblique asymptote. So in this situation, we have an oblique asymptote. Recall in previous, we had a horizontal. So when the denominator is smaller than the numerator, that means that the numerator has a little bit of say what's going on. So what we're going to want to do now is we have to divide out this bottom by the top, and we get a line. And that line, my friends, will be the asymptote. It won't be a simple y equals asymptote. It'll be y and x. They will both have to be adjusted. Now, the beauty of this is, while we could do long division, we can very simply just do synthetic. So I'm going to put 6 in there, and then we got to do 1 for x squared, 4 for x to the first, and negative 12 for x to the 0th. And then we're going to put a little, our usual. So now then, we have x squared, we've solved it out. Now it's just a simple matter of doing synthetic division. 1, 6, that becomes 10. 10 times 6 is 60. And then negative 12 plus 60 is, I'm going to make sure I'm doing it right, 48. But this 48 is going to be what is going to be a remainder. We can basically ignore this remainder. So now what we have to do is, I apologize once again for that cut. We shouldn't have any more cuts in this video. Now what happens is, as we deal with these asymptotes, suddenly the remainder becomes insignificant. We don't have to worry about this remainder. So now we just get x, well, x to the first, there's only one x, plus 10 equals our oblique asymptote. So recall that earlier when we have a horizontal asymptote, it's simply a matter of dividing the top and the bottom. And in this situation, it's exactly the same, only when we have our denominator be less than the degree of the numerator, suddenly all these other terms do have a say in how the asymptote is shaped. So our asymptote will be x is plus 10. So we just got to graph that equation. That's very simple. So then we have our y equals x plus 10 asymptote, and I did a very poor job of drawing it because I didn't anticipate that happening. So let's redraw our graph. We know that our y asymptote is going to be x plus 10, and our x asymptote is going to be 6. So let's draw a very large graph. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's going to be our horizontal asymptote. Let me just erase all these other lines because we don't need them anymore, because I didn't anticipate it being that big, but that's fine. And then this is going to be our horizontal, and then x plus 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, that's going to be our other asymptote. Now it becomes a simple matter of determining which quadrant it is in. It's either going to be up here, down here, or so on and so forth. It's going to be 3. So let's pick one for, well, we know that x plus 10, y equals x plus 10, is simply just moving the x-axis. The x point was just like that. So conveniently enough, in lines, when you added 10, you're both moving the x-axis, x-intercept over, and the y-intercept up. So we know that this is going to be negative 10 over here. So let's select negative 11 for this equation. Negative 11. Where's the equation? Right here. Negative 11 squared. We have to do this to figure it out. So negative 11 squared, I'm going to put this on my calculator. Negative 11 squared plus minus 44, because 4 times 11 is 44, minus 12 divided by 5. That equals 13. So at negative 11, we have 13, and that's well above our coordinates. So what's going to happen is our oblique asymptote is going to just look like this. And then our other asymptote, 0, 0. Well, that just means that negative 12 over negative 6, negative 2. So negative 2, it's going to be down here. So it's going to be looking like something like this. And then when x equals 7, 7 squared is 49. 49 plus 28 minus 12 equals 65. And that's well, is it? Let's see here. At 7, x is equal to, when x equals 7, y equals 70. So that's actually below here. So our asymptote kind of hugs that and then kind of trails off. So that's very interesting graph. Let me see what happens actually as x approaches negative 100, because I'm not sure about this left side. So negative 100 squared, plus minus 400 rather, minus 12 divided by negative 106. It's going to be 98. So that's going to be x equals, yeah, so I was right. It just goes like this. It's just a long parabola there, then right there it just kind of trails off. It never quite equals the axis, and this would look a lot better if I was on an actual graph with actual symmetry, but I hope you get a very good idea. Just remember to differentiate between using oblique and horizontal axis, and the methods by the rule that if the denominator is bigger or equal, then all the other terms become insignificant. But as soon as the denominator gets less than the numerator, then suddenly all the other numerator quantities that are not of the highest degree become important. So just remember that, and remember that if you have to do oblique symmetry, to use synthetic division when possible, but there might be some instances where you can't avoid it and you have to use long division. And if you do, be sure to make sure that your mathematics is correct. And you can always graph these equations on a calculator, see if you get the general idea. But bear in mind that a calculator will like to, if there's an asymptote over here, it'll like to actually draw the asymptote and move on. So if you are going to use that method, just keep that in mind and you should be good.